Hello again. This is Roger Koch Barr for the Bioelectricity course, Week 6, Segment 3. In the second segment, we were looking at subthreshold stimulation. This time we're going to move on to threshold stimulation. You recall when we were showing subthreshold stimulation, what happened was a little stimulus, 40 nanoamperes, made a little bump, but then nothing happened further on down the fiber. Move the stimulus up just a little bit, from 0.04 to 0.06. Just moved it up a little bit, from 0.04 to 0.06. Here it is, a little bit bigger. And now, wow, just like we saw before, there's a big action potential at electrode I. Still nothing at J. So we make a little sketch. We'd say, okay, what we have, here's our fiber. Right there, we have a big action potential. Down here, we're still flatlining. Doesn't seem right, but that's what we get. Over here, we see, here's the stimulus. Right there, we've seen that before on the individual patch. Then there's this period of latency, and then boom, here goes the action potential way up there. Just like before, the stimulus is an initiating event, and that results in an action potential. Well, let's make our stimulus bigger. That's always a nice thing to do. So here we go. I moved it up from 0.06 to 0.01. 100 nanoamperes now instead of 60. What happens? Well, at electrode I, this one over here, what happens is there's a diminished latency. That's how people say it, diminished latency. What that means is the time from the end of the stimulus to the start of the action potential, that little interval has grown shorter. It's because the stimulus is bigger, it seems to get things going with our action potential faster. So here is the stimulus. Then the latency, that time interval between the end of the stimulus and the start of the action potential, is now much shorter than before. And then we have the big action potential at position I. Now, what's happening over here in the middle of the strand at J? Well, it still doesn't seem like much. But, here's something happening at the end, near 6,000. Maybe there is something happening there after all. So what I've done here is I've just changed the time duration of the experiment a little bit. You notice 10,000 over here now instead of 6,000 before. Before we were doing the calculation for 6 milliseconds, 6,000 microseconds. Now we're doing the calculation for 10 milliseconds or 10,000 microseconds. I've reduced the stimulus back down, so the stimulus now is just back down to 40. And just as before, nothing happens at J. We get the little bump at I. Notice that throughout all of these sequences up until the present, there is no stimulus from S. S we have nothing, or we have this one stimulus current. Wow, but now things are different. We come up to a threshold level, and we still see our stimulus and action potential over here at I. And then at J, after this considerable delay, Here we come. And then it goes up. We have an action potential at J also. Nice. It does now what we were expecting. The stimulus causes an action potential at I. Then there's a time required for propagating from I to J. And then all of a sudden we're down here at J. And we see an action potential there too. Just want to look at that a little bit more carefully. Just looking at this trace ever so carefully as to how these action potentials are the same and how they are different. So they're pretty much the same once you get into the action potential part, but this part is different. Seems that the way they are started off is different. And we say, but of course, over here on the left, what's happening is that we have a stimulus current, and over here on the right, there is no stimulus current. Well, that seems fine as far as explaining the trace. However, it provokes another question. How does this action potential over here get started if there is no stimulus current? It just doesn't make sense. It wouldn't start all by itself. There must be a stimulus that comes from somewhere. Well, let's put that question off and ask a different question. Suppose we gave a bigger stimulus, bigger than our 0.06. Would that make propagation faster? Does a bigger stimulus make propagation go faster? If it does, then when we give a bigger stimulus, we'll see this curve on the right-hand side, the curve in the middle of the fiber, it'll move left on the time axis. And here it is with a bigger stimulus. And what we see is, well, actually not much different. Our stimulus got bigger, our latency diminished, but the time from the first one to the second one, this time interval, stays very closely the same. And I say very closely because it's hard to measure exactly, since the shape of these two is not quite the same. You don't find quite exactly corresponding points, but very nearly the time interval is the same. So stimulating harder does not make things go faster. Notice that that's different than in ball games, such as, say, baseball, great American game. If the pitcher throws the ball harder, the ball will go faster. But here we stimulate harder, that is, with greater intensity, and action potentials do not move down the fiber faster. They seem to go at about the same speed. The only difference is the first one gets started a little more quickly. So there is a shorter latency, but not a higher speed. Interesting. Well, with that observation, we'll stop for this segment. But there is more, so I'll see you again soon. Thank you for watching.